talking about
you can write, I mean, I think at some point I tried writing down all the possibilities for more read, building up more read.
Yeah.
Most things do fractions. Certainly do it.
But then I kind of, I was looking at the Devin Hutton, it's like, you know, when we go after they have these weird fractions, you know,
Yeah.
well,
You know, some people care about having physical looking construction, and some people
Okay, portrait.
have,
You're going for the
So
looks,
let's get started
not for the
with today's
inside.
talk. First, a quick announcement. In the afternoon, there will be a so-called Nudita seminar, which is somebody from the program telling the Nudita community what the program is all about. And Steve is going to do that for us. And so everybody is most welcome to come to that seminar, but if you think you know everything already, don't feel obliged to come, but I guess it will be instructive anyway. So, but that will be 1:15 in the other building. So it's a bit earlier than the talk we normally have in the afternoon. 1:15 in the other building. Which is
Not the other one.
well, no, it's the small, yeah, the one which is a clone of this building. It's in that direction.
What infectious disease is that one for?
I have no clue. it's a different one from the one here. So, and so, but I think so. But first we'll have Hugo who will give us a talk, and he's not going to talk about it, but I think he's asked if I'm not mistaken.
All right. So in fact, you know, of course, this is a new title of my talk. I couldn't resist giving it after seeing Parsons' title yesterday. In fact, contrary to what some people might think, there is a little bit more to this title than one might assume. This is the original title, implementing a single qubit phase gate in the new equals 5-half fractional quantum Hall state, and this is actually still in progress. We are writing a paper, and it's done with my postdoc David Clark, as well as with Parsa and Chayton, co at Station Q. So let me give sort of a very quick introduction into what are the basic ingredients that one needs for quantum computation, for topological quantum computation in particular. Well, for any quantum computation, you basically need a multi-dimensional Hilbert space. A traditional way of thinking about it is you span that with qubits, but the details, you don't have to have qubits in principle in order to have a multi-dimensional Hilbert space. So you hope to use this Hilbert space to encode quantum information. And the second ingredient that is needed in order to build a quantum computer is you need a set of quantum gates which are called universal if they can approximate any unitary transformation in this multi-dimensional Hilbert space with sort of any given precision. And well, there is of course a standard bête noire that sort of prevents us from building a quantum computer, and that is decoherence, which plagues all conventional. What has just happened?
I turned on the power for your computer.
All right. So you really want to hear it. Basically, there are various sources of local noise that will, in principle, decohere qubits, and by that, sort of the environment will measure your quantum states. That is, it will project try to project a vector in the multidimensional Hilbert space onto some directions that you don't really want to think about, and it will, in principle, ruin your computation. So the general idea behind topological quantum computation is to encode quantum information in non-local degrees of freedom that are impervious to local noise. This idea was pioneered by Kitaev and then quickly picked by Preskill, Friedman, Larson, and Wong. Basically, the idea is to use non-abelian anyons in order to encode this quantum information. And that's what I'm going to be talking about. But before we do this, let me give you, since I'm going to talk about anyons, let me give you a very quick crash course into general anion models, otherwise known to mathematicians as unitary braided tensor categories, but let that name not scare you. It's really simpler than it sounds. It's just a convenient language, convenient description of two-dimensional systems which have topological order in the conventional sense of that definition. So there is an energy gap, there are anionic excitations, and this description, so in principle, people think about anions as representations of the braid group, but that turns out to be not a convenient way of describing systems with multiple particle types and various numbers of particles. Representation theory is kind of ill-designed for treating various numbers of particles. So we have to resort to this unitary braided tensor categories, and the main ingredients in this description are, well, first of all, you have to have a finite set of particle types or anionic charges, if you wish. Then there are fusion rules that tells you how charges combine or split. It doesn't mean you fuse them literally. It just means is what is the combined anionic charge of a collection of anions. And of course, all of you, or many of you here are experts in conformal field theory, so what you should really think about here are the operator product expansions. That tells you how to think of several fields brought together. And there are braiding rules which specify braiding behavior of when you exchange particles. And oops, something happened. For some reasons, my pictures did not come out. Okay, I do apologize for that. So the basic idea is that you can describe, of course, something happened to the slide. What is right? So what is missing here is are the important ingredients of the anionic theories, which are, well, first of all, there are fusion rules, and the fusion rules can be typically represented graphically by essentially drawing lines, which you can think of as world lines of your anions, A and B, and you get a particle of type C. So that means that A and B can fuse into C. Now there are F matrices which you see there that enforce the consistency conditions on the fusion of particles. That is that if you take particles, well, what I'm drawing now is, well, the inverse fusion, splitting, if you wish, same kind of story. A, B, C, fusing all together in the particle type D, and there is an intermediate fusion channel E for the particles of type A and B. Then, of course, this should be isomorphic to actually fusing B and C first. So A, B, and C. So this is just the associativity of fusion. Yes. Letter. Is there an eraser here? So F, and basically there are so-called F symbols that correspond to this, which are essentially A, B, C. So these are a set of matrices labeled by what are the types of particles that you fuse together and what kind of type of particles you fuse them together. And then this is E, F. So sum over. So this is the definition of F symbols for you. This is I mean, what is written here is nothing more than the change of basis, the Clebsch-Gordon coefficient, the 6J symbols that some of you know from the representation theory. So these are the important ingredients in every anionic theory. And then there is another important ingredient that also for some reason didn't show up on the previous transparency, and those are the R symbols. And the R symbols actually have to do with braiding of the quasi-particles. What happens when you exchange two quasi-particles? So if you have quasi-particles of type A and B, and you decide to twist them around one another, you need to specify the fusion channel C, and this is actually equal to R, A, B, C, the same picture with the particles A and B untwisted. So these are the R symbols, which are the, of course, they are related to the dimensions of each of those fields, to the topological spins of each of those fields, because you can sort of imagine untwisting this by twisting each of the lines, and so there is a set of relations, but I'm not going to talk about this. All I want to say is that if I know what kind of particles I have in my theory, that is, what are the allowed labels A, B, C, and so on, what are the fusion rules, what are the F matrices and what are the R matrices, then I know everything I need to know about my theory for the purposes of this talk. Now, it turns out these F and R's cannot be anything you want. In fact, there are fairly stringent consistency conditions. One of them is known as a pentagon equation that tells you that if you have 4 particles to fuse, then there are 2 distinct paths in which you can sort of invert this tree from the right to the left. And of course, as you go through the top or the bottom path, you should end up in the same exact in the same exact final state. So, or at least the change of basis should work in exactly the same way. And so, just from the shape, this is known as a pentagon equation. There is also a hexagon equation that actually deals with the twisting, with the R matrices, and this has to do with sort of, if you wish, morphing this picture into that picture. And once again, it's graphically shown here that you can do it in 2 distinct ways. And of course, the result should not depend on how you do that. So that imposes another condition. And it turns out that given those conditions, you have fairly severe restrictions on what kind of anionic theories you can have. And in fact, Parsa and Joost, who I guess is already gone, have tried to classify all possible anionic theories by sort of essentially starting with a number of field and diffusion rules and seeing how many, how much freedom you have in having F's and R's, and it turns out not that much. But of course, the problem becomes very complicated as you allow more and more particle types in.
Can I ask you sort of unsophisticated question here from the point of view of someone who doesn't know about these tensor categories? And that is that these conditions here that you are talking about, are they automatically implemented in rational conformity theories?
I believe so.
So when you look at this more abstract language, then you're sort of considering the possibility that there would be quantum Hall states or physical states that would realize this in a way that sort of goes beyond conformal field theory. Or can, as an unsophisticated person, can I be just happy and with the little I know about conformal field theory and then be assured that these general conditions are always, implemented?
So, if I understand your question correctly, is that can you go beyond the rational theories in these theories?
No, what I'm saying is that if I'm specifically interested in the quantum Hall system, rather than the most general way of writing this mathematical structure, I mean, is it enough to learn conformal field theory? This is sort of a pedagogical problem for myself. In a
Yeah, it
sense.
is.
Okay.
But
I think actually, if you do everything in the conformal field theory direction, you end up doing a lot more work sometimes than if you reduce everything just to.
so I mean,
it's simpler.
Sometimes it's much simpler to
I-
do everything in conformal field theory and go straight to the distortion.
I think it is simpler. It also kind of corresponds to the direction which I learned this stuff personally. So for me, it was simpler. Well, basically, let me just throw a couple of useful tools, and then I'll just show how to do calculations, so you can calculate pretty much anything you want using this basic set of diagrammatic tools that I presented here. So sometimes you want to also introduce the F symbols with 2 top and 2 bottom indices that are kind of equivalent to just taking one leg and twisting it down. So it's pretty obvious what this refers to, I presume. There is a simple connection between these reformed F symbols and the ones I introduced here, which involves the quantum dimensions of each of those fields. So I don't want to go into why the quantum dimensions appear here in such a form, but it has something to do with the fact that you normalize your diagrams in such a way that you can bend lines at will. One particular consequence of this is a so-called resolution of identity that I'll use in a second. That basically is when you have 2 anionic world lines sort of running in parallel. You can, of course, imagine them exchanging an identity field, a vacuum field, which has to be present in every such theory that I denote as I, and then just use these symbols to convert the expression into this. And it turns out that these F symbols can once again be written in terms of the quantum dimensions of these fields. That's not actually essential for what I'm going to do here. Now, why is this useful? Well, this is useful because now you can do very simple calculations, such as undoing braids. In particular, if you have 2 anions A and B that you twisted around one another in the way that I did here, what you can do is you can resolve the identity the way I just showed for the middle section of this picture, doing it like this. Then, of course, you recognize the R move for each of the tops for just untwisting the picture on the top. And then after that, you can do the inverse F move, if you wish, once again propagating particles A and B. And instead of twisting with one another, now they potentially could exchange some kind of anionic charge between the 2. So by doing this, you can actually undo very complicated braiding diagrams and actually do the calculation. So that is, it allows you, given a braid, to in a fairly simple way calculate what kind of unitary transformation that braid corresponds to. And I'll use that in a second. But before we do that, let me just go back to why I need all that. So
No, I'm just asking, this looks like the Ridermeister moves that you use in braid theory. Is that?
Yeah.
It is that.
it is that. So now, well, let's go back to the ingredients that we need for quantum computation. Well, now basically the idea is as follows. So what we want to do is we want to encode the states of our qubits by the fusion channel of non-abelian anions. And the theory is non-abelian if and only if you can have more than one outcome fusion of 2 anions. That's why it's a must that the theory is non-abelian for encoding some quantum information here. So if you have 2 fusion channels for the anions A and B, then well, you can think of that as 0 and computational 0 and computational 1. Quantum gates are implemented by braiding anions around one another. So this is a complicated braid that I lifted from the paper by Layla both to, I believe Steve may or may have not been on this particular one. Okay, so you were on this particular one. So this is actually a control NOT gate implemented for the Fibonacci anyons. Now, there is another competing idea by Bonderson, Friedman, and Nayak to perhaps, instead of doing braiding by moving particles, forcibly moving particles around one another, use measurements to simulate braiding. But this is a very interesting idea, but it's not the topic I want to address here. And finally, of course, you need to measure the state of the final state of your anyons, and that's where interferometers come in, and Parsa spent some time discussing interferometry yesterday, so I don't want to...
Is it a minimal representation of CMB?
For Fibonacci anyons? Well, I believe it's not even exact, so there, I mean, Leila, correct me, but...
So what is the question?
Yeah.
So I mean, it looks very complicated, so I was asking if it's a minimal representation which you can imagine, or you can write something simple.
Well, it's an approximation to like a 4x4 matrix.
So you give yourself some error, and then it's probably a result of brute search, right?
Yes.
So if you want to have less precision, you can make it simple. If you want to have more precision, it will be far more complicated. So, now, let me throw the quote that my PhD advisor was giving me all the time when I was working with him. If we had some bacon, we could have bacon and eggs. If we had eggs, so let's see if we have any of that stuff. So I mean, why is that? I'm talking about topological quantum computation. So in order to have that, first of all, we have to convince ourselves that we have non-abelian anyons in real life. And even that is still, well, somewhat questionable. But at this point, our best shot appears to be a nu equals pi half quantum Hall state, at least our best hope for finding non-abelian anyons. And there is some numerical evidence to that extent, and Murph told us about this the other day. And then there is also some recent experimental evidence by Willett and collaborators. Parsa have shown some yesterday. I'll throw the same picture. So that's basically the device that they use, the interferometric device that has two H states, which well, can tunnel across these constrictions, and the results that people see by observing the interference of two paths is, well, basically for the 5 half states, looks kind of interesting at high temperatures. You can see the interference oscillations that you can attribute to the tunneling of the charge of E/2, but as you decrease the temperature, what you start seeing are the runs of E/4 quasi-particles, and in fact, there is, well, so we can make it slightly more precise. Here is another plot from their paper. So by eyeballing, it's kind of hard to say that this is E/2 and E/4 regions. They look sort of almost the same. If you do the Fourier transform, you get, well, kind of a broad mess with E/4 and E/2 peaks. But then if you start isolating pieces that you identify, these are actually the pieces from the previous picture, then the Fourier transforms, the window Fourier transforms look somewhat more convincing that indeed there is E/4 and E/2 present there. And if you want a favorable interpretation of this experiment that Parsa was talking about yesterday, you can think of this as an even odd effect that few people, us included, predicted some 4 years ago, which basically tells you that if there is an even number of quasi-particles inside the interferometric loop, you would see the interference corresponding to E/4 quasi-particles. If there is an odd number of particles, the interference for E/4 quasi-particles will be turned off, and then perhaps what you still see is the interference of E/2 quasi-particles that are abelian, and therefore they don't care about what's inside the loop. And so that could explain the switching between even and odd number of quasi-particles. So here's a shameless plug, a possible sort of, if you wish, favorable interpretation of these experiments. Well, in fact, we consider several scenarios there. This is a paper that is about to come out in PRB, and Parser has mentioned that yesterday as well. So we might have eggs as a result. So what kind of eggs? Well, with luck, 5½ may prove to be a non-abelian state, either Pfeiffian or anti-Pfeiffian. In fact, I don't really care which one for the purposes of this talk. This is, that being the case, it should be the Ising anion theory. And for the Ising anion theory, there are 3 particle types. Well, once again, if you want to think about Ising CFT, it's exactly the same story. So there is a trivial field, the vacuum field, the sigma, the twist field, and the fermionic field psi. And the fusion rules are given right here, with the only non-trivial one being 2 sigmas fused into either a trivial field or a fermionic field. And this is the Bracheli diagram that kind of helps you keep track of what are the possible fusion channels when you add n sigma quasi-particles together, and you see that whenever you have an odd number, it's just sigma. Whenever you have an even number, you have one of the 2 possible outcomes. In this language, the fundamental quasi-holes carry the anionic charge of E/4. Sorry, the anionic charge of sigma and the U1 electric charge of E/4. The electrons, of course, carry the anionic charge of psi. They're fermions, and the actual charge is -E. Well, n quasi-holes carry, as I just showed, the anionic charge of sigma for odd number of quasi-holes, or either I or psi for the even number of quasi-holes. So here are all the ingredients that one need to have in order to do the calculations in the Ising anion theory. So these are once again the fusion rules. These are the only non-trivial F symbols that you have in this theory. Everything else is 1. These are the R matrices that I just listed below. You can sort of ignore this. You can derive that from the data above. These are the well, I guess the topological S matrix and the monodromy matrix that Parser has shown yesterday. I don't need it now. And these are the quantum dimensions and the twist factors for these fields. So this is all the information we need to start thinking about this Ising anion theory, and we'll do that in a second. So in particular, I'll just give you a very quick couple of results that I'll rely on in a second, and that is what happens when you take a sigma particle, a sigma field, and take it around some other field. Well, if it's an identity field, you take it around. Well, then clearly you can just.
Can I ask you a question?
Yeah.
With some of those F's were -1, is that a result of the gauge choice or something?
I'm sorry?
Some of those F matrices, the ones where it just came out to be -1. Can you go back one slide?
So
Those means that there's a unique fusion. I mean, that ends up being a gauge choice or something?
No.
It's not a
I
gauge
don't
choice.
think so.
You can't remove all the
Yeah.
minus
You
ones.
can't remove
So in principle, there is a gauge involved in the F matrices, but you cannot make all of them once, if that's your question.
If you go to the integer sector of these,
So there are many of them missing here. They are ones, the ones that are not listed here. So if you start messing with this sign, you'll automatically introduce -1 somewhere else. Anyway, please pay attention to, well, actually all 3 of them are kind of important, but notice that when you take a sigma particle around identity or around the psi particle, you get a relative -1 sign. When you take one sigma around the other, aside from the phase, it's equivalent to actually exchanging a psi field between those. All right. So now let's go for some bacon, and that is what can we do with this? If we had x, let's see what else can we have here. The first idea that probably sort of started a very slew of papers, follow-up papers in this field was this paper by Dasarma and Friedman-Nayak, who proposed a topological qubit where the idea is that you have, well, what you see here is a quantum Hall bar which is gated to create constrictions, and in principle you have two well-separated antidotes. Each of them is supposed to have a topological charge of sigma, and of course your qubit is encoded in whether the two fuse into I or into psi. This constriction, this device can also act as a NOT gate, and it is a NOT gate if you you flip the fusion channel if you pass a single quasi-particle around a middle constriction. And just to show you that all these pictures that I have drawn were not for nothing. In fact, you can do very simple calculation to convince yourself that this is indeed a NOT gate. The way to do it is, well, basically, let's imagine you start in a state which is the identity, so that's, if you wish, the computational zero. That's the fusion channel for two sigma particles. These are the sigma particles that live on the antidote. And now what you want to do is you want to tunnel another sigma particle between them. What this is equivalent to is taking another sigma particle around one of them, but not the other, and then asking yourself, what happens here? So this is the sigma particle that tunneled in the middle. From the previous picture, and never mind the abelian phase that comes from this, this is equivalent to the following. So you can undo this break, and now this becomes, so this is the identity field, and this is a psi field that goes to this sigma particle. So these are sigmas. Now if you eyeball this diagram, so one important thing is that the number of fermionic modes is conserved, modulo 2. And therefore, if you started with no fermionic mode and you created one here, there is absolutely mandatory that another one comes out of here. And so what that means is that if you started with zero state, you end up in a state 1. You can flip this diagram if you wish, and that will show you that if you start at 1, you'll end up at 0. And so this is a legitimate NOT gate. Well, in fact, this is a poor NOT gate, this is a poor representation of a qubit in the following sense, that in principle, what you want to do is you want to have a qubit represented by 4 sigma particles rather than 2 sigma particles. There is good reason for that, and that is the total number of fermions, as I just mentioned, is conserved quantity. And so if there is a fermionic mode shared by if the fusion channel is psi, then there should be psi somewhere else in the system. So you might as well use two other sigma particles for that, rather than allow some knowledge about what this qubit is being somewhere in the system, and so that the environment, whatever, can measure it, which will ruin it once again. So in principle, a legitimate encoding that prevents you from, that protects you from the problem that the system has some information about the state of this qubit is using 4 sigma particles rather than 2 sigma particles. This is a detail though. Now, there was further work. Georgiev in 2006 also proposed a Adamar gate, which, well, in this 0-1 representation looks like a matrix, well, given here. And once again, using these rules, you can, well, time goes this way now. You can convince yourself that implementing these braids will give you precisely this this rule. In fact, the qubit, the logical qubit, is in the fusion channel of the first 2 lines, and 4 and 3 are these additional 2 sigma particles, as I have just explained. There is also a CNOT gate that was proposed in the same paper. A C naught is given by this matrix, so it essentially keeps the qubit if the control qubit is in 0 state and flips it if it's in 1 state. But this is a fairly poor, in fact, a C naught gate. The reason for this being a poor C naught gate is that, in fact, it's 6 line, not 8 lines, as I have just requested. So in effect, these are the 2 logical qubits, if you wish, and the other 2 sigma particles are shared by the 2 qubits. So they, I mean, you run into problems of getting into entangled states. This C naught gate is not perhaps useful for quantum computing at large. It could be useful for certain things that allow you to entangle 2 qubits, like maybe checking a Bell inequality or something like this. Now, in principle, this is all good and grand, and even the fact that this is a 6 particle rather than 8 particle representation is not really a big problem. You can fix that. It will be something complicated, but it's not really a big deal. The real problem is, well, is my title, that mu is not equal to 12/5. So, and in fact, if the BS stuff we have heard is true, then even 12/5 would help us. But the real problem is that Ising anyons are not computationally universal. Unlike Z3 anyons that might exist in mu equal 12/5 state, in which case you would be able to approximate every single unitary gate by grading those anyons. However, Ising anyons are not computationally universal, meaning precisely what I just said. An arbitrary transformation cannot be approximated by the gradient. So there is always something that you can't do with those. Now, there are attempts of getting around this, and I'll just throw a couple of pictures here. One is time-tilted interferometry by Friedman, Nayak, and Walker, which involves changing topology of your system as you sort of travel in time. So this is the picture of antidotes being sort of connected, time propagating up. And measuring the state of this connection in the middle. It's not as bad as it looks on this picture. Well, here is another picture from the same paper. So in fact, you can sort of tilt, that's why it's called time tilted. So essentially what you do is you peel off an antidote from the first one and then connect it to the second, and while measuring it in the process. So as you can see, I mean, considering how realistic this whole subject is, this slightly pushes it. So another equally realistic proposal was put by Bravi and Kitaev, and it involved the air bridges of this type, which once again, you have to change topology as you perform your operation. So you have to be able to connect and disconnect this air bridge as you go. So these proposals notwithstanding, we can't really do everything topologically, and so what we can try to do is to bite the bullet and do a gate in an unprotected way. So as I said, you have to do something in an unprotected way. You might as well, so a standard choice is implementing a phase gate. Phase gate being given by this matrix, and in fact, if you implement it with either pi over 8 or pi over 4, with all other topological gates that you can build of Ising anyons, this will make it into a universal quantum computer. Now, the question, of course, why bother at all? Haven't we lost all the advantage of topological quantum computing by actually allowing an unprotected gate? Well, as it turns out, things are not as pessimistic as one might think. There is a paper by Sergei Bravi in 2006 who came up with very clever protocols for, well, essentially fixing the problem. The point is that if you only have one type of unprotected gate, then you can allow for a rather high rate of errors for that gate, because there are ways of controlling for that error and fixing it. And in fact, in Sergei's estimates, you can allow for up to 14% error per operation for this unprotected qubit, assuming you can do everything else in a protected fashion. This is really great comparing to what the standard estimates for the error gates for conventional quantum computers are, which are sort of in the ballpark of 10 to the minus 4, 10 to the minus 5
So what
per
does this
operation.
estimate rely on?
What?
What does this estimate rely on?
So it's, you know, he just
14%.
No, he just proposed a protocol for fixing, so as long as the error is not as large, there are ways of fixing it, and then you can estimate, then you can ask yourself how many operations do you need to fix that error, and essentially there is a sharp transition between the error rate going down as you try to fix it and blowing up in your face, and so that's what the estimate is based on. But if you want me to go through the details of that, I mean,
just a comment. This technique uses up a lot of qubits, and you need to have a lot of qubits available to you to do.
Sure. So as I said, if you can do everything else in topologically protected state, you don't.
No, I mean, even if you're doing everything topological, the number of qubits you actually have to manipulate goes way up because you're using some qubits to
Sure.
distill others. And a rough estimate that we made recently is that to factor a 1/28-bit number or something, you need to fill a 10-centimeter wafer entirely densely with quasi-particles everywhere, as close together as you can possibly put them, in order to do that. This is for 128, and that's with a sort of a reasonable error rate, reasonably lower than the threshold. And it gets worse if you get close to the threshold, and it gets worse if you try to factor a larger number.
So pretty much translating for the rest of you, you can stop listening right now because it's not going to work. Thank you, Steve. No, I
mean, all proposals in quantum computation are unrealistic in some ways. It doesn't mean it's impossible. It just means it's
So feel free leaving for coffee, but for those of you who want to listen to some.
Well, do these estimates not in some way depend on knowing what's the best error correction mechanism?
Sure.
Do we have a proof that the error corrections that have been contemplated are somehow optimal?
So whether Bravi's purification algorithm is the best one there is? Yeah, it might not be, but
maybe Steve's estimate is pessimistic.
definitely pessimistic in some sense.
Well,
all right. So here is the standard law.
The future is long.
Yeah, about 20 minutes.
Perhaps you should turn off the camera.
So anyway, people were thinking about, if we could just somehow fudge this phase gate, then perhaps this whole idea of topological quantum computing could still work with the Ising anyons. And the standard law that is in many papers, I don't want to cite all of them. I don't think I ever said that we ever said that in any of our papers, but well, this one is lifted from Jack, Friedman, and Walker, and there are equivalent statements in many other papers that I've seen, is that, well, basically, that the energy of different fusion channels is degenerate as long as you keep the quasi-particles far apart, but if you start bringing them close to one another, there will be splitting in the energy levels, and, well, then perhaps we could just judiciously bring the quasi-particles close to one another for some time, move them apart. While they were close to one another, because of the energy splitting, there would be a relative phase accumulated in one of the states with respect to another, which is, well, given by this standard quantum evolution. So my claim is that it's not really a good idea, despite being listed again and again. And the reason why it's not a good idea is actually kind of interesting. This is the plot of the energy splitting between two fusion channels for the Pfaffian state that just recently came out. I don't know, has it come out in the PRL yet, or about to come out by these people, including Steve Simon here. While they propose that you focus on this part of the splitting for the short distance, I suggest that you look at what happens further away. And what you see further away, and it might look like an error to you, but it isn't, is that the energy difference actually oscillates as a function of distance. And also notice the characteristic period of its oscillations. It's roughly a couple of magnetic lengths. Now, is that a fluke? Is that just what happens for the Pfaffian state? Well, I think it's actually generic, because if you look at the estimate of delta E for the P plus IP superconductor, that has been done by also very recently by Cheng, Luchin, Galitsky, and Dasarma, and also either just came out or is about to come out in PRL. They got an analytic expression that, aside from the exponential part, also has this cosine. And so it just seems to be a generic behavior that delta E is actually an oscillatory function. And what sets the period of those oscillations is some short-range physics. In this case, for P plus IP superconductor, it's the Fermi, it's the Fermi momentum of the original metal from which you started. In the previous example that I had here, so I asked Steve, well, I mean, here you can see that it's coupled magnetic length, but for this probably is once again the Fermi momentum for the composite fermion Fermi C or something like this. The point is that it is some kind of short-range physics over which you have no control over, and so trying to implement a gate which relies on the precision, so you don't even know the sign of your phase unless you can get the precision of essentially a couple of magnetic length.
Isn't it just a matter of being able to do something repeatedly? I mean, if you go in, you add a phase, and as long as you can make the same, as long as you can go in and make the same phase, you measure it once, and then you know.
Yeah, so the question is whether you can calibrate such a device.
Yeah.
You might be, but I think this is a pretty...
I don't think the oscillations cause you any additional trouble than you would have had even if it was non-oscillating.
Well, if you didn't have oscillations, you could hope to sit somewhere in the exponential tail and say, well, the phase changes very slowly, I move a little bit to adjust it. Here the phase changes very slowly, but the sign of that change changes rather rapidly with you moving particles around. So, you might come up with something clever, but I think it's actually, a pretty bad thing for trying to implement the qubit in that way. I might be wrong. So what we propose is, what we hope is a better idea, the T-bag or the sac geometry that is sort of adopted of the wormhole designed by Howe and Shimon. No, I personally hate the word wormhole. Don't ask me why they called it that, but I think the idea is, well, basically this is the picture lifted from their paper. Never mind what's inside this sac. So the point is that this represents the edge of a quantum Hall liquid, and basically there is a single constriction that allows quasi-particles either stay on the edge and sort of move along, or hop from one side of this constriction to another. Well, that's the reason for calling it a wormhole, I presume, because by doing that, a quasi-particle can move faster than it would otherwise move along the edge. But no, I'm not backing that name. Now, in our case, what we would like to do is essentially put a qubit here, and so the proposal by Shimon was to actually try to detect non-abelian statistics. They were thinking of having or not having a sigma particle inside this the sac. What we would want to have is actually two sigma particles or a full-blown qubit inside, and now try to see if we can rotate the state of this qubit by sort of passing quasi-particles along the edge as that happens. And so I just listed the, since we are now dealing with the edge, I just listed the edge modes that can live here. So this is the 1/4, the E/4 quasi-particle, which consists of a twist field of a sigma, and also the charge corresponding to E/4. There is also a Laughlin quasi-particle, the 1/2 charge quasi-particle, which is a pure charge mode. Of course, there is also an electron field, if you wish, and that's the fermionic mode times the charge. So you may say, well, how do you know what actually propagates and what tunnels across the edge? And in fact, this the whole mess goes along, of course. But the one point that I want to make is that the only edge excitations that have a non-trivial effect on the qubit are the ones that carry topological charge sigma. So the fact that there is these two excitations, the types of excitations that might as well be shooting along the edge, is completely irrelevant to the operation of that qubit. Now, you can also see that, back from the pictures that I have shown, that if you sort of look at the interference of a sigma particle that went along this way and just jumped across, it picks an extra factor of -1 if the qubit is in the state psi with respect to vacuum state. So by looking at the interference of particle going here and particle going here, you can actually get the some information about the state of the qubit. But of course, we are not looking. So in fact, it's not really measuring anything because a quasi-particle has no other option but to tunnel all the way through. So the only thing that is affected is its phase, and therefore by the phase of a qubit. Now, you can sort of do a simple, so you can treat this as a simple toy ballistic model and ask yourself, well, if you shoot a quasi-particle and ask yourself, well, what is the phase that accumulated by this qubit as a result of a single quasi-particle that can either tunnel with the amplitude t or go around the edge, and take multiple reflections into account, because in principle what can happen, excuse me, is a quasi-particle, it can either tunnel right away, it can go around and then go to the drain if you wish, or it can tunnel back and just repeat the circle. So taking those into account is fairly simple, and the answer you get is that the phase in this phase gate, the phase accumulated by one fusion channel with respect to the other, is given by this expression where this phi AB is just the Aronoff-Bohm phase that the particle picks going around this region.
And that's assuming coherence is kept.
Yeah. So I'll get back to that in a second. This is just a toy model, just to see how this this gate would operate. Now, if you want a full-blown answer, and in fact this is not even a full answer, you need to do an edge theory calculation, which you can do at finite temperature, and that will take care of all the coherence effects that you asked. So basically, you start with the Lagrangian, with the standard H Lagrangian for the Ising theory. That is for the Pfaffian theory. It consists of a charge part and the fermionic part, and you added perturbation, and the perturbation, this is the tunneling perturbation, it essentially connects the twist fields at points -a/2 and +a/2, which are the coordinates of the constriction, and that's the charge part of that. And so all you need to do is to, well, or at least the simplest thing you can do is treat this, well, the only thing I know what to do with this Lagrange is treat this perturbation, well, in order by order. And in the first order, all it does, it shifts the, it splits the energies of the qubit a little bit, resulting in the accumulation of a phase, which sort of, the expressions leading from here to here are not pretty, but fairly standard, because all you need to do is do a first order perturbation theory. So all you need to do for that is to calculate the, just take the conformal block for the sigma fields. Of course, that depends on whether the charge inside the sac is 1 or psi, because that determines the fusion channel. You can do that at finite temperature. That's just a conformal transformation from plane to a cylinder. And voila, here comes the answer. That might not be particularly enlightening, but you see that, well, it depends on the temperature. And of course, so the important thing is that it depends on for how long you keep the constriction open in your system. Alpha is the phase, is both the Aronoff-Bohm phase and the phase of the of this gamma matrix element. That in principle will also depend on time if you change the geometry of your constriction. Now, oops, something is strange with my. Okay, there was another transparency that doesn't show up. It's probably good that it doesn't show up, because that one showed the estimate of an error, of a variance in theta, which is a much messier expression, because for that you need to go to the next order and deal with 4-point correlation functions. But the point is that at this point we have the expressions for both the phase that is accumulated in this device and for its variance that we need to know. The equation for the variance is really messy, so it's good that you don't get to see it, and in fact it can only be evaluated numerically.
Don't you have this exactly the same problem that alpha is going to oscillate on the order, the phase of the tunnel is going to oscillate on the order of the magnetic length as you change? You would expect it has the same 2kF oscillations as you.
I'm not certain why KF shows up here at all, because this is already a long-range theory.
It's the same. So then if you ask what the phase of the, so the reason we find the splitting between the two quasi-particles is because there's a, if you think of a tunneling matrix element between them, there's a phase associated with that tunneling matrix element. And here you have a tunneling matrix element with two edges, and you assume that there's a phase which oscillates as 2kF on that matrix element.
The oscillations that you found before were tunneling in size, right? We were telling something, so they might not be the same, but I kind of see this.
So I actually cannot answer your question, because one thing that we are still doing is actually plugging the numbers and trying to see what comes out, although I don't know how we can possibly plug any numbers here.
In Dasharma's paper, it was called PX plus IPY, isn't it?
The Sarmas is PX plus IPY.
Yes, and here is the Duke of Battle.
No, but in their paper it wasn't. In their paper it was Puffian,
Yeah,
and you get the same basic
I'm not
behavior.
sure if there's 2kF behavior.
Yes, so parallels.
Parsa, do you think that the oscillation might die off and you wouldn't have zeros anymore, zero transitions? It would the oscillation die and lead to a no sign change after some distance?
You mean in this as your?
Yes.
I mean,
is that your idea?
I think that you probably can do it, but I can't say with 100% certainty.
Yeah, that's what.
So the oscillation might actually die off, and you'd have a uniform approach to zero without oscillations. That's an interesting possibility, of course.
It might not be the same.
No, No, Steve, it might be. It's actually a good point, and I don't have an answer to that. So that pretty much concludes my talk. I didn't put any conclusions because at this point there aren't any.
Further questions? I mean, we have now looked at the problems that we would have with these easing. Can we expect that the Fibonacci case is so much better behaved if we look at it in more detail? Could it suffer from defects that we just don't know about at this point? I mean, I understand that the universality that one can somehow expect or perhaps prove might be something that's extremely desirable, but do we know that there won't be other traps?
So, I mean, Stephen Layla would be better qualified to answer that, but my impression is, well, so one advantage of the easing theory is that aside from this phase gate, the other gates are actually extremely simple, or relatively simple. That is not the case for the Fibonacci's. So if you really need to use the conventional type of gates with the Fibonacci anyons, the braids that you've seen grow kind of long, that means that you have to do lots and lots of manipulations in order to get. So it doesn't have to be the problem, because it's the question about the quantum compiler in a sense. Do you need to actually use conventional gates and therefore this very complicated sequences of braids in order to implement the quantum algorithm? But if you were to go the standard route, that would be the the most immediate drawback of using Fibonacci is the length of the braid. And of course, if something goes wrong, it goes wrong. I mean,
if you were to allow phase gates in the Fibonacci theory, can you shorten those gate algorithms?
Phase.
What do you mean?
So the same thing. So the same thing.
Oh, but you
But then-
want to say because you have it.
but then it feels like you lose the only potential advantage of Fibonacci is if you were
You
to.
don't need it, but if you were to include it, could you sort of condense the whole thing somehow?
I don't think so, because then you need to insert error correction. I mean, the main difficulty in
So there's no
by far
no point in trying.
you're spending in all these systems, you're spending 99% of your time
Yeah.
or more on error correction, so you don't want to introduce errors.
Are you saying that the Fibonacci case would not need error correction?
In principle, it won't.
Is that a safe statement?
The future is bright. And the future is long.
The future is long, I agree.
Well, to begin with, at this point, there is some flimsy experimental evidence that easing anyons might exist. There is none
Of course.
that the Fibonacci's might exist. The gap, our best estimates from just experimental measurements of rho XX, is that the gap is by the order of magnitude smaller for the...
That is a dangerous argument, I think, because I personally think that the gaps of an intrinsic system without disorder, whether we can get close or not to this limit is another question. But I really believe that the intrinsic gaps, the ones that are not suffering from disorder, are not that dissimilar. They are very close, I think. And I think the main reason why we don't observe what is calculated for the intrinsic gaps is the fact that quasi-particles are able to tunnel through the saddle points. The saddle points are not very wide on the scale of the wave function that describes this excitation, the charged excitation. Charged excitations are huge. You may remember that I gave you...
Are they bigger in 12/5 than they are at 5/2?
Yes, they should be even bigger at 12/5. We don't know how big they are really, but they are already huge at 5/2. I said
I mean, they would be
of the
bigger
order of
if-
100
if
nanometers.
the
And
PS,
we shouldn't forget
varied, but
we shouldn't forget that the setback distance in present-day samples is of the same order as the width of these quasiparticles. Quasiparticles are 100 nanometers. The setback distance is typically 1,000 100 nanometers, 1,000 angstroms in these symmetrically doped quantum well samples, and that sets the scale, the lateral scale of the disorder, to the same length as the quasiparticle size. And that's why we get the strong quantum tunneling. We don't have to cross the barriers. The barriers get chopped off because the quantum tunneling is very strong. It's going to be very strong. If we had different samples...
Here is your potential drawback for implementing anything then...
Well,
with Bernacchiani.
the samples have not been optimized to have no quantum tunneling. They have never been optimized for that. They have been optimized to see higher mobility. It's not mobility that decides whether we see intrinsic gaps or not. It's a different mechanism that leads to the small activation gaps.
Anyway, you might be right. It would be good if that were the case, but at this point, no.
We don't have it.
We don't have that.
We don't have that. But we have indications that this is true because we certainly know that symmetrically doped samples where it was possible to go to higher densities without going closer with your dopants have much better... remember the first experiment by Willett in '87. There was no gap. As you lower temperature, the rho XX just became a constant with temperature. It remained non-zero, whereas in later samples, subsequent samples, Jim Eisenstein was able to determine a activation gap of the order of 100 millikelvin. In the meantime, this has gone up by a factor of 5 to 540 in the Joy sample. It's the same density, but the disorder effects are different. Factor of 5. And again, the future is long. We'll see better samples that will get much closer to the intrinsic. I'm sure about that. So if the gaps are not too dissimilar for the 12/5, and if the 12/5 was of the kind that we like, that would not be, I don't think, against...
On the other hand, if it turned out to be the way Barca likes, then well, we're back to this problem.
I'm not opposed to Fibonacci.
There's no further questions? Then let's,
I know, of course. No, look. Are you saying this is the most unrealistic approach?
okay. And now it's recording and then you just press again.